You know, forecasting the weather for TV1 means that wherever I go, people ask me, how's the weather, Jim? Well, over the next hour, I'll show you just how difficult it is to answer that question. Why, for example, it's wet on that side of the mountains and dry on this side. At least I won't get asked that question up here.
Hey, how's the weather, Jim?
How's the weather, Jim?
How's the weather, Jim?
How's the weather, Jim?
Hey, how's the weather, Jim?
How's the weather, Jim?
How's the weather, Jim?
How's the weather, Jim?
What's the satellite dish this buoy and a jumbo jet got to do with weather forecasting? Well, like this weather balloon, they're all used for gathering weather data. But just where does our weather begin? Well, it begins with that up there, the sun. And a good place to find out what happens is in here. Now, here we have our model, not to scale. Sun, Earth, New Zealand down here, and the moon. Notice how the sun's energy, solar radiation, that's heating and light, strikes the Earth. North Pole, South Pole, equator. Now, as the Earth rotates or spins, we get our 24-hour cycle, day and night. Day, night. But as the Earth orbits the sun, we get the yearly cycle, the seasons. Autumn, winter, spring, and summer. New Zealand down here. Now, what's important for weathercasters is where the sun heats the Earth. Notice how solar radiation strikes the poles very obliquely, so there's less heating there, but it strikes the equatorial region more directly. Come with me to that region, and I'll explain how that has a direct effect on our weather. Now, it's near the equator that the sun does its most intensive heating, and that's what kickstarts our weather patterns.
Hey, Jim, how's the weather?
So why are the tropics often described as the birthplace of the Earth's weather? Well, as we saw, most of the sun's energy is received at the equator and less is received at the poles. Nature tries to balance things up by transferring heat towards the poles. Got that? Good. Now, these heat transfers and air shifts cause bubbles of high and low pressure to form, which interactively produce wind. New Zealand's most prevailing winds come from the west, and this is a major factor in the makeup of our weather. The result? The westerlies and the roaring 40s. So we get this hyperactive mix of highs, lows and fronts, which are simply boundaries between different air masses. The location and shape of New Zealand has a direct effect on our weather. We're isolated and surrounded by sea, which has a huge influence on what we get. Not only that, the makeup of the landscape is diverse. From the Southern Alps to the Canterbury Plains, from Mount Taranaki to the forests of the far north. It's a geographical tapestry as diverse as the weather it shapes. Now, the presence of a mountain chain extending the length of the country has a major effect on our regional climates and produces much sharper climatic contrasts between west and east than it does from north to south. In some inland areas of the South Island, just east of the mountains, the climate is distinctly continental in character, with large daily and seasonal temperature extremes, despite the fact that no part of the country is more than 130 kilometres from the sea. Here in Ophir, central Otago, we have the biggest temperature range in New Zealand of 55 degrees Celsius. The lowest temperature recorded was -22, and of course in high summer it's into the 30s. Is there anywhere else in the world where rainfall and vegetation differences are so large over such a small distance? I don't think so. From rainforest to semi-arid desert in less than 100 kilometres, to more than 7 metres of annual rain in Fiordland, to less than half a metre here in the dry basins of central Otago. Well, all these variables, landscapes and topography, rainfall profiles, pressure and wind differences, make New Zealand's weather a little bit of a forecasting nightmare. After the break, we look at the multitude of microclimates across New Zealand.
Being a sailor, I'm a great believer in the saying, red sky at night, sailor's delight, red sky in the morning, sailor's warning.
Statistically, it rains most often in the month just after the full moon.
For those off fishing, when the wind's in the east, the fishing's least, and when the wind's in the west, the fishing's best.
When the seagulls flock into flat fields and gather around, we know it's going to be bad weather.
You always know when the bulls start to get a bit frisky, the wind's going to turn a bit bad.
How's the weather, Jim?
How's the weather, Jim?
You know, the weather is a little bit like a river. It has a beginning, sometimes just a little flow. It gathers momentum. It's got a few rough patches like storms and depressions. It has calm spots like the still pools in a river. And it has an end. Weather systems peter out, just like the river reaching the sea. And then the cycle begins all over again. Evaporation out of the oceans, condensation as the clouds form, and precipitation as the rain falls out of those clouds into the hills. Our little stream begins its life all over again. Now, location and topography, that's the shape of the land, means that we don't have constant climate in New Zealand. In fact, we get all types of weather, much of it packaged into tiny local identities we call microclimates. Now, as we've already seen, the prevailing wind is from the west, out there, straight off the Tasman Sea, and that's a key factor in the sort of weather we get. And nowhere is that more clearly demonstrated than on the west coast. The highest recorded daily rainfall is 682 millimetres at Collier's Creek in the hills above Hokitika, where the mean annual average is more than 6,000 millimetres. That's over 6 metres. Now, by contrast, in Manawatu, Otago and Southland, daily totals of more than 80 millimetres are very rare. So why is it so wet on the west coast? Before we answer that, have you ever thought about how rain forms? Sure, like snow or hail, it comes out of cloud. But it all begins with the old evaporation, condensation, precipitation formula. Let me demonstrate. Electric jug, you've all got one of those. Full of water, turn it on. If you pass heat over or through water, you get evaporation. Now, if we lift it to a cooler level, got an oven tray up here, you may have one of those as well. Let's get a bit of stuff out of the fridge. Organic diced carrots and put those up here. So this is our cooler level. Okay, so this is where the cloud, if you like, the condensation, the cloud development will take place. You watch. Now you see what's happening here. Of course, we're boiling the jug. Already we're seeing little tiny wee droplets, like cloud particles, forming on the bottom of our cooler layer. If you like, you can imagine a cooler layer of air. Here, of course, we're using our frozen peas and stuff to get that coolness. So the condensation beads are developing quite quickly. If we keep the lifting, the cooling and the condensation going, those tiny weedy water droplets, like cloud particles, stick together, grow and fall as precipitation, rain. Now, a similar thing happens here as the humid westerlies off the Tasman Sea hit the Alps. The air laden with water vapour is forced up, cools and expands and causes the vapour to condense into tiny droplets or cloud particles. With more lifting, cooling and condensing, droplets grow, join together and heavy rain falls. At the same time, the sun's energy, which evaporated the water in the first place, is now released as latent heat. Now, once all that rain has fallen over there, there's very little left for over here. What was a wet wind over there becomes a dry wind over there for the Canterbury Plains. Remember that latent heat was released as the rain fell? Well, as that dry wind descends on the lee or the eastern side, it becomes compressed and warms up as it moves into higher pressure. It becomes the hot, dry, firn nor'wester. It's a strange one, this. and it becomes even more complex as we head down over there. Here in Christchurch, there's a weather phenomenon, a strange, spooky wind that seems to affect people. It's called the nor'wester. Similar winds are experienced in Switzerland, Israel and Los Angeles. It's a hot, dry wind from the northwest. But why does it affect people? Well, here's a man who's got the answers. Neil, question. How does a wind that begins as a moist, cool one traverse a mountain range and arrive in Christchurch as a hot, dry one? How does it go through that metamorphosis?
Well, it actually is the sun shining on the Tasman Sea evaporates the moisture. So solar energy is converted into evaporated moisture.
Yep.
It hits the mountains, gets forced up over the mountains and rains, and that solar energy is released into the air again. So the air that comes over the mountains, as it comes down the other side, the pressure increases, it compresses it again, but it's warmer than it was before. And because it's rained on the west coast, it's drier. So we have warmer, dry air. It's very turbulent air, and it whips across the plains at quite high speeds. And static electricity builds up.
Yep.
And so a lot of people notice they get shocks when they open their cars and things like that, because the air is charged, it's getting onto your body, and it builds up the charge on you and goes back to your car. But we found that that was the mechanism for causing health effects.
Examples of errant behaviour. Have you got some examples?
Well, teachers say kids can't be controlled in classrooms. They just get so excited and
hyperactive.
Oh, very, very hyperactive. But of course, it's the teachers also who are feeling irritable and can't concentrate. So over day and night, the symptoms build up. So some people notice the symptoms very quickly, but by the third day of a nor'wester, typically 60, 70, 80% of people can feel the symptoms.
Getting irritable,
yeah,
tired, listless.
Yep. But there are some people who get excited and feel elated. There are about 15% in our surveys. They went up when you had a nor'wester, but the vast majority go down.
I guess it's a good thing that a nor'wester generally only lasts a day or two, then it's gone through.
Yes, yeah. But on occasions they do last as long as a week. And boy, the police say they have problems. And that's because they say to us, oh, it's hot and dry, so guys drink much more. And when they drink alcohol, they become violent. They go home.
Absolutely.
And the kids are wild, the mother is irritable, and they find a problem, and so there's more domestic violence.
Compounded.
Yeah, so it's a compounding of whole lot of effects.
So we're quite right in saying it's a strange, spooky wind.
Oh, yes, definitely.
So much for Christchurch. Here in Queenstown, the summers are hot and the winters are cold. Sunbathing in summer, skiing in winter. It's what we call continental weather, much the same as, say, Central Europe. Generally, though, New Zealand's weather is classified as oceanic temperate, tempered or modified by the sea, so it's mostly mild with long sunshine hours. But because of Queenstown's distance from the sea, it has this continental weather pattern. Another Kiwi peculiarity is windy Wellington. Question, why is it so windy here and over there in Cook Strait? Well, imagine a river held back by a huge dam. You punch a hole through the dam and the water is forced through with tremendous force. Similar in New Zealand, with the Southern Alps over there and the Wellington Ranges here damming up the westerlies. The hole in the dam is Cook Strait. It's a pressure release valve, and the wind speed funneling through here is dependent upon the air pressure building up on the western side. Here in central Waikato, there's a different weather phenomenon, fog, which is basically clouds sitting right down on the ground. Now what happens is the cold, dense and heavy winter air rolls down over the wetlands and onto the river flats where there's lots of water vapour. The ground surface, which is even colder because it's lost all its heat by radiation, chills that water vapour down to its dew point and causes it to condense into tiny windy cloud particles. Bingo, fog. But it's not all extremes. Big parts of our country have fairly constant weather. They have their own localised, packaged weather systems. We call these microclimates. Big parts of Hawke's Bay, Marlborough, Central Otago, and even here at Waiheke Island are all good examples. That's why they're suitable for producing grapes for one of our biggest export earners, wine. And in Te Puke, growing conditions are ideal for a Kiwi icon, the kiwi fruit, because the fruit loves late spring, early summer rain and winter chilling to help the bud break and, of course, the flower numbers. And there are lots of other examples right across New Zealand. Oranges and kirikiri, for instance. You see, the weather largely determines what we grow and where we grow it. However, you can cheat things a little bit by creating your own microclimate, just like these guys have done right here in Karaka, South Auckland. Not only that, the weather determines where we can keep these old beauties, because cows thrive in warm weather with good soil and reliable rainfall. Unlike the merino sheep, which don't like the ground too wet, they like the high, dry environment. Auckland, of course, has got a notorious climate with a whole cluster of microclimates. Why is that? Well, it's on such a narrow stretch of land. We call it an isthmus. On this side, we've got the Pacific Ocean, and not too far away, over here, we have the Tasman Sea. So the relative humidity is always pretty high. Plus, we get the sea breeze convergence off each of those ocean masses. We get a lot of uplift, a cloud formation, and changeable weather. 4 seasons in one day, as many say. So we have this huge diversity in our climate, and we've adapted to it pretty well. But we still need to know what the weather's going to do tomorrow and the next day, and maybe even next week. How do we do that? With forecasting. And how does that work? Stick around.
How's the weather, Jim?
How's the weather, Jim?
Yes, we're all familiar with this, the weather map. What does it all mean, and how do we get the information to forecast the weather? Well, I'll show you. First of all, the gathering of weather information. All over the country, weather data is constantly being gathered in a whole variety of ways, including weather radar, automatic weather stations, environmental data recorders, and weather balloons. And not just in New Zealand. Data is gathered from all around the world, and New Zealand has access to that data through the WMO, the World Meteorological Organisation, to which we belong. That data is then fed into central computers, and forecasters analyse that to prepare their forecasts. So just what is some of this data gathering equipment? Let's start here at Whanuapai Air Base, just north of Auckland, where one of several weather balloon launch sites is situated. So, Morris, this is the kit, the radio sonde that goes up twice a day from Whanuapai?
Yes, we send them up 10:30 in the morning and 10:30 at night.
Now, this has got a lot of gear in it, and it includes a little probe here, of course, includes what, temperature readings, humidity?
Yes, the little thermistor on the end there records the temperature. The second one down here with a cap on it records the humidity.
Yep.
And there's an inbuilt pressure sensor inside.
So temperature, humidity, pressure. What about wind?
Wind is detected by the GPS unit on the back here, Jim. Let's try
a GPS unit?
Yeah, I'll just get it out. And there's a little device, aerial and GPS unit.
So look at that. So that connects with the GPS network?
Yes, and detects the wind every second of its 100-minute flight.
That GPS or global positioning system lets Morris know exactly where the unit is during its flight by receiving signals from satellites way above the Earth, and thus measures the drift and the wind speed. Clever, eh? So we packed up the transmitter and balloon and went across the airbase to the launch site. And because the balloon is filled with hydrogen, well, it's well away from anything else. Good old easterly to get it on its way, Morris. Be out over your place in no time.
Not too much rain, which is good.
Next up, connecting all the components. First, the balloon is connected to the hydrogen supply and carefully laid out.
We take care not to touch the balloon because that could affect the burst height. Oh, Jimmy, put the plastic bag over my hand.
Then the radio transmitter with all its measuring equipment is simply tied onto the balloon.
Yeah, as the string of wire unwinds, it'll probably get down to about 150 feet away from the actual balloon.
As much as that? Then the launch pad is secured and it's off to the control room.
Okay.
The blast off zone.
Right.
All okay? Yeah, she looks all right. Good.
Go for it.
I know. And off it goes up to 100,000 feet. As the balloon rises, so the transmitter package unfurls to 150 feet below the balloon, so the balloon itself doesn't interfere with the readings. During the ascent, the transmitter continues to send back data to med-service automatically. The flight time is about 100 minutes. At the top of its climb, the balloon expands and bursts, and the transmitter package falls to Earth or into the sea. The $300 cost is written off, and it's worth noting that most of the gear is biodegradable. Did you know that there are 7,000 ships all around the world that voluntarily report weather information? And 40 of those ships report data from around New Zealand. This, the spirit of competition, is one of them. John is the ship's second mate with the job of collecting the weather data. Very important data too, both for shipping and for us on terra firma. The equipment for collecting it is loaned to the volunteer ships by Met Service.
Well, this is the aneroid barometer. This measures atmospheric pressure. This is a barograph measuring atmospheric pressure also. The pen gives us a reading over the course of a week on what the atmospheric pressure's been. But important for us, it gives us a 3-hour interval there. We've got a wet and dry thermometer in here. Between the difference of them, it gives us our dew point.
So we have 40 ships gathering weather data from the seas around New Zealand. And up and down the country, we have 60 of these. Automatic weather stations. Trevor is the Met Service technician, whose job it is to look after all 60. This one is at Levin, just north of Wellington.
The temperature is sensed inside the white screen there. The reason for using a screen is so that we're only measuring the air temperature. We're not measuring any heating effect from the sun. Up on top of the mast, Jim, we've got our wind measuring equipment. On the right, we've got the anemometer measuring wind speed. And on the left, we have the wind vane.
Now, what have we got here?
Well, we've got some more temperature probes, Jim. Down here, we've got a grass minimum probe, and that's where you're going to get your frost measurements from.
These ones?
They're measuring earth temperatures at different depths. Over here, Jim, we've got equipment for measuring solar radiation. It's called a pyranometer, and what it does, it's a photodiode, and the output's dependent on how much sun shines on it. Yeah, this is what we use to measure the rainfall. We know the area. The rain's channeled down into a seesaw arrangement with a bucket on each side, and because we know how much it takes to fill the buckets before they tip, we now know how much rain we've got.
And even the Met man's got to have a shed.
Yeah, we've got to have a shed.
Bloke's got to have a shed.
Yeah. In here, Jim, we have the weather station itself. It's a computerised data logger. The data from the sensors comes in on the right-hand side here.
Yep.
You see all separate cables, one from each sensor. Into the data logger itself. It's a computer processor and sends the data off to our Kelvin Weather Centre once an hour via a modem.
Well, so much for automatic weather stations dotted around the countryside. There is a marine equivalent, and Julie from Met Service looks after the New Zealand network. Julie, just what is this bit of gear you've got here?
This is a meteorological drifting buoy that sends weather information, weather data from sea back to Met Service.
And how big is the network of these that you use?
We try to keep 7 of these going in the Tasman Sea, Jim.
How important is the data collected by buoys floating around the Tasman Sea to New Zealanders?
It's vitally important, actually, that we receive data from buoys and ships, because all of the weather for New Zealand is coming from the west, from the Tasman Sea. Also, we have forecasting responsibility for a very large marine area, and this information helps greatly for verification of marine forecasts.
Now, even a jumbo jet provides frequent data on wind and temperature at high altitudes. But what's that got to do with us at ground level? Well, one man who's been flying jumbo jets for many years is Captain Pat Scotter. Pat, tell us about the weather equipment you've got on board and how the data is sent back to base, so to speak.
Well, this aircraft, Jim, is really an airborne weather station. We can receive information from the ground as well as from the ambient area that the aircraft is in. We can record the wind velocity and direction and the temperature at the altitude that we're at anywhere in the world, and that information can be automatically sent back to the air traffic control services, and the air traffic services can provide that to the Met authorities if they require it. Further than that, we can pick up thunderstorms on our radar, which is very similar radar to the radar which the Met services use on the ground for local use. And by using the radar, of course, we can avoid giving people a bumpy ride.
Meanwhile, back at Air New Zealand base ops,
the upper air data comes from the aircraft automatically into our flight planning system. Our flight planning system then transmits it automatically again to Kelvin in Wellington.
And this is Met Service headquarters at Kelvin, overlooking Wellington Harbour. On the roof, the all-important satellite dishes. Satellites, Bob, are such a vital part of weathercasting. What do these ones do specifically?
Right, the dish focuses on the satellite way out there, quarter of a watt over 36,000 kilometres. We get from that eye in the sky, it's got these little infrared cameras on board and it can see the cloud top temperatures night and day. And it sends us information every hour so we can see exactly where the clouds are coming from, globally, which is just right. But we've had satellites in the sky for 30 years now, as long as I've been forecasting. And nowadays we've even got satellites with microwaves on board. And the microwave can measure the wind over the sea.
Doesn't cook a meal for you?
Doesn't do that, just the wind over the sea, but it's great, new advances, because finally we can see wind and rain over the whole globe all the time.
Well, now we have all this data and information. So how does one forecast the future based on historical information? And of course, a view of what's happening at the present? Well, we're about to tell you.
How's the weather, Jim?
How's the weather, Jim?
It's at Met Service headquarters in Wellington that all the data is collated and the weathercasts are prepared. Okay, once the data's here, what forecasting tools do you use to turn it into a forecast format?
Right, well, when we collect the data, we can put it on a map and draw it and work out where the isobars are, the pressure lines, and also looking at the satellite loops, it shows us how the clouds are moving in. Radar's really good because it shows us where the rain is and we can watch it coming in and moving away, which is great. Now, with the data, we can pass it over to the computer, mathematical model, and extrapolate the data into the future. And 1 day, 2 days, 3 days, maybe out to 5 days into the future. And it, unfortunately, because of the chaos, that kind of interferes with the pattern. And so we can't go much more than about 5 days using our known mathematics.
The nodding, as it's called, is our forecast conference, and that we have these 2 meetings at 9:30 in the morning and at 10:30 in the evening. And at those 2 meetings, we decide what the forecast policy is going to be for the next 12 hours especially, but 24, 48 hours.
Yeah.
Okay, is everyone happy up to midnight tomorrow?
Yep.
Now here at TVNZ, we get that correlated information plus the Met Service predictions sent to us via computer feed. And then it's up to us to rework and interpret that information into the forecast that you see on your screens every day.
And cue Jim.
But what happens when the weather turns to custard?
But I drove down the road, pouring rain. Suddenly the rain came sideways at me and it was like somebody chucking stones in my face, and I tried to, sitting on the bike like this, tried to pull the bike up and turn my head away from it because it was so strong, and just, I virtually had the bike pulled up when it was like a giant vacuum cleaner, just wham! I was just sucked clean into the fence in front of me on the road. The bike went hurtling away one way and I went spinning up into God knows where, and my worry was the power lines across the paddock. It didn't seem to be up there very long, and wham, I landed on the flat of my back. From where I sucked into the fence to where I landed on my back was about 100 metres away.
So, Laurie, show us exactly where the tornado picked you up and where it dumped you.
It was out on the road where I got flung out, and I landed just over in front of the farm cottage there. And by the time I got up, of course, it was just devastation.
So Laurie was very lucky. But back in 1948, lives were lost right here in Frankton on the edge of Hamilton when a tornado ripped through the area. And the old bike shop behind me here was one of few buildings in the area that stayed intact.
Just before midday on August the 25th, a tornado hit Frankton Junction and Hamilton East, causing 3 deaths and many injuries, and leaving a devastated track through shops and houses.
So just what exactly is a tornado? Well, simplistically, it's a wildly rotating column of air, like a big cylinder, if you like. And you usually find them at the base of our biggest, meanest, most aggressive cloud type. That's the cumulonimbus or thundercloud. And what happens is the huge updraft at the base of the cloud sucks up air rotating near the Earth's surface. It then mixes it with cold downdrafts, or the air spiralling down out of the cloud, and you get this entwining of air currents, a little bit like the strands on a piece of rope here. Up near the tops, these CB towers can grow to 12,000 metres, where the air temperature can plunge to -50 degrees Celsius. and it's there you get this vigorous activity which produces thunderstorms, thunder and lightning, and hail. So much for thunder, tornadoes and hail. What about snow?
Even wild deer, normally able to cope with the harsh conditions, have been floundering. If the predicted frosts begin over the weekend, the near whiteout conditions covering some parts of Canterbury could remain for weeks.
Well, unfortunately, weather conditions for that area are going to worsen, and Jim will have the details later.
Now let's remember that snow results from the lowering of the freezing level, usually when a cold polar southerly undercuts warm moist clouds which have been brought down from the subtropics by a low or a warm front. The cloud particles freeze into tiny ice crystals, and these coalesce or join together and grow, and thus the snowflake is formed. It's a far more gentle process than the violent updrafts and downdrafts we get in a thundercloud, which can lead to the formation of hail. Speaking of which,
in just 5 minutes, the storm left a trail of destruction across Hawke's Bay. Huge hailstones pounded the region. Driven by strong winds, they shattered panes of glass. Hardest hit were apple and pear growers around Hastings. Some were ready to begin picking tomorrow.
As dawn broke on Saturday, the people focused on a drama they couldn't have dreamed of. By Monday morning, for many, the terror had passed, and it was time to count the cost.
that cost? 1,000 kilometres of wrecked fences, 50,000 dead livestock, 600 hectares of destroyed crops, and $16 million of damage to property. I'm standing in Lake Pukaki, South Canterbury, one of the country's main hydro storage lakes. Usually, the lake level is up around that black mark along the rocks there. Here we are in late winter, and look at the lake level now.
Damage right along the coast is estimated in excess of $20 million, including devastating stock losses.
It's been a long, hot summer. Brilliant blue skies, but down below, a baked earth.
I think to farm in this area, you've got to be pretty resilient anyway, and you've got to farm for a drought every year.
Storms, cyclones, tornadoes, drought, snowstorms, floods. All extreme weather conditions and all experienced in New Zealand in recent years.
The thing is, we've got some of the most changeable weather in the world, and therefore our forecasters have got to be top-notch to be able to cut the crust and to try and work out what's going on. Remember that weather, although it's a natural resource, can also be very disruptive, especially in New Zealand. We try and help people. We try and help people to brace themselves for disruption.
Chris, regarding extreme weather events which come up from time to time and the impact they have on agriculture, what's MAF's role in that?
Not as comprehensive, Jim, as it was 20 years ago, but nevertheless, MAF is particularly sympathetic, anxious to give the farmers as much warning as possible, but really doesn't get involved unless the local community finds it beyond their possibilities to actually cope with the situation. And the 97-98 drought, an El Nino drought, which first struck in Marlborough, spread right throughout the length of the East Coast. I can remember at the time government being very keen to ensure that the country had 3.5% GDP growth. In fact, that didn't transpire, and it didn't transpire because agricultural production really dragged the chain, not just for that year, but for the years following as well. It's a biological system. You put the rams out to the ewes are in poor condition, they don't lamb, and the impacts the following year. The cows are very light, they don't milk well the following year, the wool isn't clipped till the following year, and so on. And so there is a lag effect, yeah.
So much for our weather. What about our climate? Is it changing? Some say it is. After the break, I'm off in search of the truth.
How's the weather, Jim?
How's the weather, Jim?
Now, what I hear you say has the Sky Tower got to do with climate? Well, I'll tell you with the help of Georgina Griffiths from the National Climate Centre. And that's a division of NIWA, which stands for National Institute of Water and Atmosphere. On the way up to look at Sky Tower's lofty connections to our weather, I had a question. So, Georgina, your definition of the difference between weather and climate?
It's all a matter of timescales, Jim. Weather is, what do I wear today? Shall I paint my house this week? Climate is much bigger picture, longer term. We had an ice age 25,000 years ago, we certainly don't have one now, and the climate of Auckland is wetter and wilder than, say, for example, Christchurch. Yep. And Wellingtonians don't own umbrellas, they have coats.
Very good. Well, here we are on the upper observation deck, the sky deck, and of course there's quite a bit of weather data coming through on the monitor here. Now, Georgina, where's this stuff coming from?
Well, some of it comes from right up the top on the Sky Tower itself. We run 3 data streams that come in via this television.
Is that right?
Yep.
Up on the steeple? Up
on
there,
the steeple?
On the knitting needle.
Okay.
Now, NIWA, I know Met Service deals with day-to-day weather, what's happening in the atmosphere, the troposphere, what have you. NIWA, of course, looks at a much bigger picture. What exactly do they do?
Okay, well, we do pretty much everything. We're one of the leading providers of environmental science for New Zealand, and that's pretty much the seas, the skies, the environment in between. So if you want science, you come to us.
Historical data.
Yep, that's one of the things we do. We remote sense in the environment. So we put gadgets out, they record the environment as it is now.
Okay.
But for some things like climate change and a lot of the fisheries things, we actually do a lot of modelling, a lot of science and forecast what's going to happen.
Getting back to this stuff, can we have a look at these instruments?
We can, way up the top. Come on, let's go. Harder than I thought.
Well, here we are, 300 metres above the ground in a howling northeasterly gale, Georgina. What are we doing up here?
I was going to ask you that, Jim.
Tell us about some of the instruments you got up here, what they do.
Okay, we've got 3 types of instruments up here. We've got wind sensors, which measure wind speed, of course, and wind direction. We have air temperature to find out what the ambient air temperature is up here, and we have an ozone meter.
And what does that do, the ozone meter?
It measures low-level ozone, which is an indicator of how dirty the air is right down there.
Can you monitor these instruments from your office in Auckland here?
Yes, we prefer to do that.
Come up here.
The data are pinged via radio or a landline into the office, and obviously in the Sky Tower themselves, they can look up at a screen and see these data coming in.
Important to have instruments this far up?
Oh yeah. I mean, these are obviously weather equipment. They're used for weather forecasting, for example, and for the tower operations themselves. But in a climate sense, the Sky Tower is a really important record. It's a clean air site, okay? We're not affected by trees growing around, by other towers, springing up, although that might happen in the future. The wind is the free air, it's great, and the temperature, it's not affected by the urban heat island effect. That means when the cities get a lot of asphalt, a lot of warm things happening, a lot of people living in them, they actually get warmer. And if we're looking at climate change, a climate record, we have to get away from that.
Something that many people have heard of, but few fully understand, is the El Nino and La Nina weather phenomena.
Of course, the sea is the big signal.
And the Pacific Ocean is a key factor in whether we get one or the other, or neither. Georgina explains. Typically, what happens for us in New Zealand in an El Nino?
Typically in New Zealand we would have more southwest winds than normal, but if we get more southwesterlies than normal, places in the south and west get wetter than normal, and it dries out in the eastern areas of our country.
In that situation, El Nino, with the southwesterlies, it's not uncommon, is it not, for droughts to appear in places like Hawke's Bay, North Otago?
That's correct. I mean, often we have a shift in probabilities during the El Nino to drier conditions in the east. But you've got to remember, Jim, it's very important. Not every drought is associated with the El Nino. It just means that there's a higher likelihood of that occurring.
What happens in New Zealand when the eastern part of the Pacific seems to be a little warmer than usual?
In New Zealand during the La Nina, we have a lot more northerlies and easterlies. That typically brings like warm and humid subtropical air down onto our country, and that's why we're often much warmer than normal. That's fine. But for places in the north and east of the North Island, there's another effect. We're often a lot wetter than normal. We get a higher chance of tropical cyclones during the season, of course, and meanwhile the South Island is often under a lot more higher pressure than normal. It's often more settled, and it tends to dry out during the La Nina down there.
What about occurrence of each of those events? Have we had, say, over the last 2 or 3 decades, more El Ninos than we've had La Ninas, or does it balance out pretty much?
If you look at, say, the last century, it has balanced out. Usually La Nina, followed by the El Nino, bit of a flip-flop pattern. But there's been something quite interesting that has occurred since 1977. We've experienced more El Ninos since that time. And so people on the west coast of the South Island, of course, have had more rainfall than normal, and eastern areas have tended to dry out. So you should really believe the old-timers when they say it used to be, it's got wetter on the west coast.
It's a bit wetter than what it used to be.
Yeah, so the old-timers are right.
They're onto it. In a nutshell, Georgina, is our climate changing?
It is, Jim. Our climate's always been changing. If you look at any climate record back into the past, there have been large fluctuations there. Some of them are natural. In fact, there are a large number of natural ones, such as the Earth, our orbit around the sun and the tilt of the Earth. That's a biggie. The sun's energy is a big one.
There's so much talk about global warming. Is it happening?
Yes, if you look at long enough records back, you can see that it's happening. We've warmed up so that the 1990s were the warmest decade in our record, and 1998 was the warmest year we've had on record. Since mankind started the Industrial Revolution, we believe that's linked to a huge increase in carbon dioxide, which is a greenhouse gas, in the atmosphere.
That was the mid-19th century.
It was.
Right, can the bloke in the street notice any discernible change in what the climate's doing?
Yep. We can. The person in the street can notice two things. They can notice normal climate fluctuations that would occur if there were no global warming. They would notice that in 1950s, for example, and 60s, the weather in New Zealand got a lot warmer and it got more settled in certain regions. And they'd go, gee, the summers in my youth were really nice. Okay. Since 1977, there's been another natural climate change, which has meant that it's got wetter in the west and south of New Zealand. But there's also been the global warming signal there, which we believe is discernible to the person in the street. And that said, we're very, very warm now. The rate of warming is huge, and you know, we don't have the nighttime frost that we used to have. Our daytime temperatures have gone up somewhat, and you know, you and I, we would notice it, particularly farmers.
Getting further up, the ozone layer. Why do we get sunburnt real quick here? It must be related to that.
Yes, we have low levels of ozone, but there are places that have lower levels of ozone. It's the clarity of our air though, Jim. It's our nice clean environment has a drawback, and that's one of them.
So New Zealand's not really exposed to any more ozone depletion than anywhere else in the world, but it's ironic that we get sunburn here because our air is so clean.
Yep, the UV can come all the way down to the surface. It doesn't get filtered out like in the Northern Hemisphere. The latest NIWA predictions are that New Zealand is in a better shape for global warming than the rest of the globe, okay, than the global range.
Why is that?
Because we're surrounded by sea, and a lot of that expected heating, for example, would be modified or neutralised by the waters around New Zealand. So in 100 years, we're going to be 2 whole degrees.
Warmer?
Yep.
On average.
And let me give you an example of what that actually means. That's the difference between Auckland mean annual temperature and Wellington and Christchurch. It's like moving Christchurch to Wellington and Wellington to Auckland. So big impacts, not just on what we wear, it's on what we grow, where we live, how we live, our whole lifestyle. So a very big change. 2 degrees might not sound like much, but it's a huge,
very significant
huge change.
That's 100 years from now.
Yes, it is. But the good news for New Zealand is that our sea level rise, which is predicted for 2100, given the current state of knowledge, is that we're likely to be less than the global average sea level rise. And what we're talking around is approximately 40 centimetres rise for New Zealand.
So weather and climate are inextricably intertwined, and it's through the network of satellites, ships, automatic weather stations, weather buoys, jumbo jets, radar and the best computer systems around that forecasters make their increasingly accurate predictions.
There's probably 3 places which are the worst in the world for weather forecasting: Falkland Islands, New Zealand and Britain, because they've all got a lot of sea just upstream of them.
So how's the weather? Changeable and changing. That's how it is.
This program was made with funding from New Zealand On Air.